In this video, we'll be talking about homeostasis and feedback mechanisms that help to regulate internal body conditions. First of all, many animals have certain mechanisms within our bodies that help us to maintain relatively constant internal conditions. And the term that's used to describe this is homeostasis. Homeostasis translates to steady state. We'll talk later about how it's not actually keeping things exactly set at a certain point, but keeping them within a certain range. And so when changes outside occur, the body is able to respond to those changes by doing different things inside to help maintain those internal conditions within that normal range. Under most circumstances, that's the case. So essentially, the way that the body maintains this relatively steady state, homeostasis, is by going against changes that occur. So when a change causes a value, like maybe body temperature, to go outside of the normal range, homeostasis kicks in terms of turning on certain effects that cause them to go against that change, to bring it back here within that normal range. And so it's important to note that homeostasis isn't just bringing things back up, it can lower or raise levels to get them back within that normal range. We'll talk about a few examples that will illustrate this process. Excuse me. So the body, mainly through the brain, is constantly monitoring the brain and the rest of the nervous system, constantly monitoring our internal body conditions. And when a change is detected, like I said, there's some corrective mechanism to go against the change that takes place. The conditions get back to normal, back into homeostasis, and those corrective mechanisms are shut off. This is part of what's called a negative feedback mechanism. Negative feedback mechanisms are going to turn off that process once the imbalance has been corrected. So the information, the end result that's happening from these mechanisms feeds back in and causes these mechanisms to shut off so they don't continue going forever in that direction. And this is the most common way that our body helps to maintain homeostasis and responding to these changes. So here's an example with temperature. So body temperature, normal state is approximately 98.6 degrees Fahrenheit, 37 degrees Celsius, within, degree or two of that. And so let's say that you exercise a lot, right? And so the stimulus here, your body temperature gets above normal because you're exercising a lot and you're getting hot. So your body doesn't want that to happen. It wants to stay close to this normal range. So what happens is your body responds by doing a variety of things. Sweating, increasing the diameter of blood vessels that are going towards the surface of your skin. And by making these wider blood vessels, you get more blood flow. That's why your face feels warm, your ears, you might turn a little red. And that's going to allow heat to kind of escape more easily from the surface of the skin when blood is closer to the surface. Because of these responses, the body temperature drops. That negative feedback then results in saying, okay, we're back to normal. Let's turn off these mechanisms up here. Oppositely, let's say you go outside, you're not dressed properly in the winter, your body temperature gets below normal. How do you respond? Well, one way is that your hair might stand on end, producing goosebumps. In other non-human animals, that can help to trap heat, but we've lost too much of our body hair through evolution. It doesn't have that effect anymore on humans. Instead, one of the things that we do is we shiver. Oops. You shiver, right? When you get cold. And shivering is muscle contractions that are generating additional heat to help warm up the body. Also, up here we said blood vessels widened, right? They widened. And now here's the opposite. Blood vessels are going to constrict, they're going to narrow. So less blood is going to the surface of the skin. That reduces heat loss. So more of that heat then is going to stay deeper down inside the body. As a result, body temperature increases back up to normal. Once it gets back to normal, negative feedback shuts off these responses and homeostasis is maintained. So here's a quick question about this. So we have two heat maps here. Red is showing 37 degrees Celsius. The other colors are related to different colors here. You can see that when it's too cold outside, the body prioritizes keeping our core warm because that's where all of our vital organs are, because it can't afford to keep the entire body warm. So it's like, all right, we got to sacrifice something. And so over here, we have environment A and we have environment B. I want you to take a minute to compare these two and look at which of these diagrams, A or B, do you think represents the homeostatic response of an individual exposed to cold temperatures. You want to see which of those match with what's going on here in this individual that is outside in a cold temperature. So go ahead and pause it, take a minute to consider that. Okay, hopefully you've had a chance to think about this. So if it's cold outside, you do not want blood flow going more towards the surface of the skin, because you can see here then a lot of heat's going to get lost. You would get even colder. Instead, this is what's going to happen here, right? Blood flow going to the surface of the skin is going to be reduced. So these blood vessels are going to constrict. And we'll talk about what arterioles and stuff are in a later class. But the blood vessels, it's a type of blood vessel, becomes narrower. So less blood is going to the surface, close to the surface, less heat is lost, keeps that individual as warm as possible. I want you also to think about when you exercise that you are going to be sweating, and so if you continue to exercise, you may feel thirsty. So I'm not going to give you the answer to this, but think about how feeling thirsty during exercise is an example of a negative feedback loop. So we've talked about maintaining internal body temperature. We're going to talk next about maintaining proper acidity of the blood, the pH. And then in class, we'll go through how our body maintains a normal blood sugar level. So one very critical thing to note down here in the bottom left is that, like I said, homeostasis does not involve keeping conditions exactly the same. So static means unchanged. It doesn't keep them unchanged. Instead, it keeps them, as you can see here, within this range, right? Around what's considered normal. So that's kind of this natural physiological tolerance within those limits. There are certain times, though, when the conditions are so extreme that your body can't maintain it, and it may lead to damage to your body or even death. Like here, these individuals doing this polar plunge where they decide to jump into freezing water, close to freezing. If they stay in there for too long, their body cannot maintain homeostasis, and they would go into hypothermia and eventually would die. So let's talk now about pH and how our body maintains the pH. So first of all, most of the reactions in our body happen in water. Water is a great solvent. It's excellent at dissolving all kinds of things. The only things that can't really dissolve in water are things that are non-polar, like fats, for example. And so we call an aqueous solution, that's the term we use, is something when there's a substance dissolved in water. And in any aqueous solution, some of the water molecules, a very small number of them, actually split apart. Remember, water is H2O. That means there's two hydrogens and one oxygen, right? So they'll split apart, where one of those oxygens was with one of the hydrogens, and the other hydrogen over here is all by itself. This we call a hydroxide ion. You can see I've listed that up here. And the H plus is we call a hydrogen ion. A hydrogen ion is a strong acid, and hydroxide ion is a strong base. We'll talk about what that means here in just a second. So how concentrated these hydrogen ions here are in an aqueous solution or aqueous solution determines its pH, a measure of its acidity. So we're looking specifically at hydrogen ions as a measure of acidity. The pH scale typically runs from 0 all the way up to 14. It can go beyond that actually in both directions, but you typically don't see that. And then 7 would be in the middle. So 7 is the pH of pure water. That's neutral. We don't say that's an acid or a base. Anything lower than that, we consider to be an acid. So acids have a pH lower than 7, between 0 and 7, which means they have a higher concentration of these these hydrogen ions. So what is an acid? An acid, as you can see up here, is a chemical that when you put it in water, it releases these hydrogen ions, causing more of those hydrogen ions, greater concentrations, to be present in that liquid. A base, on the other hand, has the opposite effect. It removes those hydrogen ions. It reduces their presence. It lowers their concentration. So bases have a lower hydrogen ion concentration, and their number is greater than 7. So now let's get into the body. How does the body regulate pH? Well, one thing that's used are these chemicals called buffers. Buffers are chemicals that can act as an acid or as a base. And what I mean by that is they can act as an acid by donating or releasing hydrogen ions, or as a base by removing or accepting those hydrogen ions. So let's take a look at that. So here we're going to look at the blood. And the buffers within your blood are going to counteract any changes in pH. So for example, when you exercise, remember you're going to be breathing a lot more, and you're going to have more carbon dioxide actually that stays in your blood. And so your blood's going to become slightly acidic when you exercise. So if that gets too low, what happens is these buffers in the blood act as a base, and they take these hydrogen ions and remove them from that solution to reduce the acidity, which means if the acidity is being reduced, it puts the pH back up towards normal, which is slightly above 7, so slightly basic. Now, something else could happen that could cause your pH to become too basic. Maybe you're hyperventilating, you're not actually getting enough carbon dioxide into your blood. And so if it becomes too basic, now this chemical buffer can act as the opposite, as an acid releasing hydrogen ions. So over here it's acting as a base because it's absorbing or removing those hydrogen ions. And here it's acting as an acid. So it's able to do both. And then that one is going to lower the pH by bringing it back down to normal. An important thing to note is that buffers do not cause the pH to go to 7. Some might, but not all. Buffers cause the pH to go to whatever is considered to be normal. Okay. So buffer causes pH to return to normal. And normal is not always 7. In the case of blood, it's slightly above 7. It's like 7.3, I think, or something like that. Previously, we've learned that the stomach secretes acid. It's a very strong acid, somewhere between pH 1 to pH 2, approximately as strong as battery acid in a car. Not quite, but close. And so how come our stomach acid doesn't just eat away at our stomach itself? Well, there are two things in our stomach that protect it. One is a layer of mucus. And this layer of mucus creates a physical barrier so that acid cannot come in direct contact with the cells down here below. Additionally, these cells secrete buffers, and the buffer is going to help to neutralize that acid to keep the pH, in this case 7 is normal, near 7. So that's not going to get too acidic, and that protects it. Now, sometimes that protection gets eroded, and that can lead then to acid coming into contact with the stomach lining, which can eat little holes or wounds in the stomach lining. We call those ulcers. The most common cause of this is a certain bacterium called Helicobacter pylori. You don't need to know this for this class, but this is the cause of, I think, like 95% or more of ulcers. We didn't realize this until relatively recently, but that means you can take antibiotics to get rid of a lot of ulcers. However, there are other factors that can contribute to damaging the protective features of your stomach. Could be overusage of NSAIDs. NSAIDs is non-steroidal anti-inflammatory drugs, things like ibuprofen, aspirin. Too much alcohol or caffeine can also lead to some damage potentially that can make you more susceptible to ulcers. Usually, it's this bacterial infection. Another thing related to acid is heartburn, also called acid indigestion, or a more pervasive problem called acid reflux. So we'll be doing pig dissections later in the semester, and when we do, we'll find that the esophagus is where food goes down into the stomach. When it approaches the stomach, it will encounter one set of sphincter muscles that regulates the passageway of food into the stomach, and then prevents it from being able to come back up in that direction. Well, sometimes that sphincter doesn't close all the way, and stomach acid gets back into the esophagus, literally burning it. That's what we call then heartburn or acid reflux. So here's a few questions. I want you guys to pause the video here and take a minute or two to go through and answer these 3 questions. Okay, so if you haven't paused the video and done it yet, go ahead and pause it. I'm going to go through the answers now. So you've got acid indigestion, and you're trying to figure out what could help you. And so it's asking, of these 5 options, what do you think would be the most helpful? Well, you're not going to want something else that's very acidic, because that's not going to help. Coffee is also slightly acidic. So now we're down to these 2 options here, water or Alka-Seltzer. Well, what you want here is you want the Alka-Seltzer, because Alka-Seltzer is a base, right? It's above pH 7. And if you combine a base plus an acid in the right amounts, and the right concentrations, you get water. Salt water, but water. So what happens is it neutralizes it. Base plus acid, that neutralizes the acid. So question 2, which liquid from the choices in question 1 is the most acidic? Well, lemon juice has the highest pH, so that's the strongest acid. And then the only pH I'll ask you guys to memorize is that of distilled water. You should know that distilled water, pure water, is a pH of 7, and so that would be the only one that's neutral, pure water. So to finish up this topic, we're going to talk about 2 things. One is how even a 1-point change in pH is actually very significant, because if you look over here on the far right, let's say you've got something like water that has a pH of 7. Okay? And let's say that means there's 1 hydrogen ion there. There's a lot more. We'll say there's 1 hydrogen ion. Okay? Something with pH 6 has 10 times that. Something with pH 5 would have 100 times what water has. pH 4, 1,000 times. So every 1-point change in pH is equal to a 10-fold change, factor of 10, in the concentrations of the hydrogen ions. So there's 10 times more hydrogen ions for every 1 point step in pH going down in terms of acidity. That means, in common terms, for example, that if we compare tomato juice to lemon juice pH 2, tomato juice pH 4. Lemon juice is 100 times more acidic than tomato juice is because it has 100 times more hydrogen ions. Now, how did I figure that out? Well, let's take a look here. For this question, we're comparing soda and coffee. So coffee has a pH of 5, and soda has a pH of approximately 3. And the question is, how many times more acidic is soda than coffee? So what I'll do is I'll write in the other number that's in between these. Every 1 point change is a factor of 10. That means going from 5 compared to 3 is 10 times 10, or equals 100 times. So pH 3 is 100 times more acidic than coffee. Soda is. So go ahead, pause the video and try to answer this question to see if this is sinking in. Okay, hopefully you paused the video. Let's go ahead and take a look at this. Again, I would advise you to do it in this way to make sure you don't miss any steps. So we'll write out all the numbers between 3 and the other thing we're comparing. 4, 5, 6. And we're talking about pure water, which remember that's a pH of 7. So we're comparing these. Each step, we'll put an arrow in. And that's a factor of 10 for each difference between one number to the next. So 10 times 10 times 10 times 10. That's going to be a 1 with 1, 2, 3, 4 zeros after it. That means that something with a pH 3 is 10,000 times more acidic than water is. One final problem related to pH. Go ahead again, take a minute, pause it, try to solve this question. Okay, so here we're considering pH of 6.5, again compared to pure water. I'm also going to put pH 6 in here, and I'll show you why in a second. So we know going from 6 to 7, right, that's a factor of 10 times difference. But we're not at 6. Instead, we're comparing this 6.5 compared to 7, right? That's the comparison we're making there, okay? And so pH 6 would be 10 times more acidic than 7, but 6.5 isn't quite there. And so the first part to this is figuring out that 6.5 is more acidic than 7 because it's a lower number, so we can cross off the less acidic ones. And now to be 10 plus times more, it has to be a lower number down here. Like, in the 5 range or the 4 range, those would be greater than 10 times more. Cross that off. So it's somewhere in between 1 to 10 times. We know it's more acidic than 7, but it's less than 10 times more acidic, and so it's somewhere in that range. So with maintaining homeostasis, we've talked about negative feedback. And negative feedback counteracts a change. When something gets back into its proper range, that feedback will shut off that system. Positive feedback is the opposite. Positive feedback is moving a system away from its starting state, further out of homeostasis. This is usually a temporary mechanism, and then negative feedback kicks in to shut it down. But positive feedback is like more, 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 and we'll talk about a few examples of that. Negative feedback, again, is counteracting it, shutting it down once that process has been counteracted. So one example of positive feedback is with bananas or other fruits that ripen. So when fruits ripen, they release a gas called ethylene. You don't need to know that detail, but they release this gas. And this gas causes other nearby fruits to also ripen. As they ripen, they release more of the gas that causes more fruits to ripen, releasing more gas and more and more. And so that's an example of positive feedback because it amplifies that process. Another example is with childbirth, with labor. So what happens is as the baby grows, its head gets bigger and it begins to push and stretch out the lower part of the uterus called the cervix. That stretching is received by the brain as a signal, causes this hormone called oxytocin to be released. Oxytocin travels back through the bloodstream to the uterus, causing the muscles to contract. That pushes the baby down. That pushing stretches more of the cervix, which causes more hormone, more pushing, more stretching, more hormone, more pushing. And so the contractions get stronger and at quicker intervals until the baby comes out, and then negative feedback kicks in and shuts it off, right? You don't want to have contractions go on forever. It stops it once that part is achieved. The last example we'll talk about here is with blood clotting. And we'll get into this in Unit 3, but a blood clot is a way to use these little sticky things called platelets to plug up a wound so you don't continue to have blood loss. And what happens is initially there's a small number of these platelets that are attracted to this injured site. And what happens is those platelets are going to attract chemicals that attract more platelets. And then those more platelets are going to attract more release more chemicals to attract more platelets and more and more and more until this plugs up. And again, eventually, negative feedback kicks in and shuts this off once that wound is blocked because you don't want that clot to continue to grow and grow and grow and block the whole blood vessel. And so again, down here it's reminding us that positive feedback is usually temporary. And it's usually part of a larger system that incorporates negative feedback that then will shut that whole thing down once that positive feedback of more and more and more and more has achieved its goal. And that should, I think, finish up this topic.